Hello again, friends. So, apparently I'm British. I guess it's not the first time that's happened, but yeah. So today I figured I would focus on complex type signatures or how to read type signatures in general. And this is kind of a bit of a weird one because it's not real. I wouldn't call it theory based. It's more instructional, but it's more just like the tips that I have for how to not get frightened by massive type signatures. And now, I will say it's not actually too often that you run into a type signature that just confuses the heck out of you. But it is definitely possible. And so today I'm just going to show you some examples of that and show you that there's really only, as complicated as things can get, there's only a couple actual pieces to a function in any case. And we'll kind of start from the simplest possible case to more complex cases. So a good example would be our plus signature, which is going to be num of a. And so what this is saying and how this reads is that A is a type which is created from an A and an A. And, we all intuitively understand what plus does, but what is this type signature saying? Well, it's not, this is, again, not the same thing as just A to A to A. We have a constraint. We actually have two constraints, really. One, that A must be of the num type class. So if we were to look at the info for num, and there's going to be many more, as we saw, when we were looking at Haskell for the math lesson. But it must be one of these types that fit into place. And so when we do that, we can reduce it from num A to A to A to word, for example. So it'll look like word to word to word. And so, either we're doing this, we are stating that when we are using plus in a given case, like we could do some sort of type annotation where we literally just say, I could have a function. I guess this is the easiest way to do it. F equals plus, and I just make my function. I'm just gonna do that. F equals plus, and I'm gonna say word to word to word. And that's one way we can do it, by reducing it down to that. But the other restriction is that all of these need to be the same type. So, and the reason for that is because they're all using this polymorphic type variable of A. So a non-example is if this was B, that would mean that we can do plus with an integer and a float, and it would return, in this case we were saying, if this is the int, this is the float, then I guess we return an int. However, that's not the case. We are saying that we have to add together two of the same type, and we will get that same type back. And it will follow this sort of, the method of addition, whether that be a certain numerical type or another. And really, this is, in a sense, as complicated as the shell of a function or the shell of a type signature gets. We have some constraints, and then we have some arguments, and then a final return type. And so although we're, using an arrow kind of in an overloaded sense, to say that we have multiple arguments and we return this last type, it's not, that's actually not even really true to say, because in a more complicated explanation, which you don't really need to understand, we are only applying one function at a time. And so we would apply A into this A to A to A, and then we would apply that result into the A to A. And so we're always really doing one singular function, or using one singular argument where it's A to B in the most general sense. And that takes us into our type signature of a function, which is just simply this. You don't have to write it this way. You can also write this in front of the A, but that's effectively what's going on there. But anyways, if you don't want to think about it in that formal a way, you can just think of it as whatever comes after the last arrow is our return type, and everything that comes before that is going to be an argument. So of course we'd have, in our plus head, we'd have A and B, and then this body would return something of the type, A, or whatever I was going to say C just because of the numerical ordering, but it would return something of the type A. So, but yeah, everything just really builds on this simple type signature, and you could really, you could even skip the rest of the lesson and just use that sort of notion, and you will be good. Now, let's add in a bit of complexity here. We might have, for example, a maybe A. And so we still have two arguments and a final return function, or final return type. This still means that A applies to this A here, even though it's wrapped in maybe. It still applies a constraint on A, given that it's the same, type variable. And then, same thing with these guys. And really that's it. We can make this some other constructed thing, like either, where we have either BA, and then we add, and I guess we've also added here another type of B. We could also make it A here, I guess, if that makes it simpler to think about. And now I guess another complicating thing that we could do, and I guess I'm just going to call this now F, just for generic sake. Let's say these were all B's, and this is still even the same case, but what we're doing is we are restricting the return type. And now I'm not really sure of an actual example of this. Off the top of my head, I believe there are examples in the math prelude functions, like from integral, for example, would return from integral. Looks like, so it was num A, and then it was integral B. We had B to A, and so we have a constraint on B and a constraint on A. So where the return type has to be of num. Now, and so I guess also in this case, we've kind of introduced another bit of complexity that still fits the same basic mold of what a type signature for a function looks like. And we just added a different constraint, a different type class constraint. So both of these, of course, are just type classes, right? Everything that appears on the left side of this sideways house, I've called it just for fun. This, this arrow, this special arrow, whatever you want to call it. I don't know. I don't know if there's an actual legitimate formal name. I don't really care. And yeah, so everything to the left side is going to be a type class constraint, and so of course, it has to be a type class constraint on a variable on the right side. So, for instance, if I said C, then this would complain. Let's see if I even did F. F is of the type num C. Now I try to say A. And then I call. So F is just going to throw its arguments and return us a string. It doesn't really matter what I'm doing here. I'm just doing that so that the compiler can tell me that this will fail. And it's saying could not deduce numC because there's no such, or the type variable is ambiguous. There's no such thing as the type variable C in the following type signature. So any of these type class constraints, we can therefore say must be about some type in the following signature. And so let's say we, just kind of enumerating through the ideas of what's possible. Let's say the constraint was only of num. We can't say num AB because, well, and we'll actually, I should explain that part. Num AB, we'd have to say instead num B, and that's the reason for that is that if we look at num, so we have this kind of notation here that the type of num, and so this is kind of a bit. Actually, that's even, I would say, argue a bit advanced in terms of what that is. I mean, this is really, so I think we can still understand this pretty easily, though, if we have gone through the kinds lesson. You don't really have to think about that constraint so much, that constraint keyword. You might even be able to kind of guess what that means. But it's really in the same sense that, the key part is this segment in which it's saying that it takes a singular argument. So if we were to give B here, we're saying that it gets a second argument, which is just not true. And so we can still have a constraint on B, but we just have to add a second constraint. And so, and there is such a thing now as constraints that are, say some type class, and it looks like this. And so this would, I believe this would actually bring in a language extension, but again, I'm kind of focusing on how you guys are reading, in the wild, as opposed to what you might make. It probably not for a while that you'll be kind of writing your own type classes where it's some sort of complex relation between two different type variables. So just want to make sure I'm not misexplaining something here. And I guess that's really it for that kind of point. And let's go and actually look at some. So I have this first one here, and this is kind of an easier one. We have a bit more complexity in that this is just a bit more of a complex type. But again, as you can see, and really start to train your eyes, Haskell, I kind of see Haskell as a visual language, no pun intended. Sorry, I gotta pause for a sec. All right, sorry about that. Roommates came home from the bar, so in this case, yeah, the only real added complexity here is that map is a more complex type. So if we look at, and we can by the way do info for any construct in Haskell, whether that be a type or a class or a function. I think, yeah, right, you could say this for a function. It would just give you, it wouldn't give you too much. It would give you kind of all that there is to know about it. Interesting. I don't remember ever seeing that. Well, I guess that's because it's a type class function. But if I was to say type or info on elem, yes, I don't know why I did that. Then it would tell me the, elem is, we're just going to delete that because we haven't gotten to that yet. So if I look at the info on ID, there we go. So yeah, it would show me where it's defined as well, and it just will give me all the information there is to know about some construct, including where it's defined. Now, so in the terms of map, if I import it from data.map, this is because I don't have the package in my Cabal folder. You know what? And I haven't done that kind of way in a while, so I'm just gonna add it here. So that is a pretty useful library. Right, I had to quit Cabal REPL. I'm going to pause this because I accidentally leaked a kind of the last part of the lesson. So yeah, about as which was so that even before we get to that, like that's like way more than you even will ever need to read. Yeah, way more than you will ever need to read. What I have highlighted there is a very low level function that it is kind of cool. It's able to generalize just a ton of different phenomena, I'll say, without, how do I get non-jargony, but yeah, it's complicated because of good reason, I guess is the best way to say it. But it is definitely complicated. But also, it's complicated so that very simple high-level functions can be written on top. And so, the main point is you won't need to read a function like that. You might need to read a function like this. You definitely will need to read a function like this. And so let's break this down. And how I would read it from start to finish, assuming, this is, I will say, very easy for me to read. It might not be, it might be scary, fair enough. Like, I definitely would have had challenges with reading this at first. And, and that's really what I'm sharing here is my kind of strategies to sort of read any type signature and how to break it down systematically. Because I am also interested in understanding these kind of low-level, complicated, or complex types or functions. So we can see just from reading from the kind of right side first that it's going to return us a map with a key, some type which is going to be a key, and some type which is going to be a value. Now I guess I know what those types actually represent, but it's a map KV is going to be return, where K and V are polymorphic types. And I can see, there's a constraint on K, so this element of the map. There's a constraint on the key, which is saying that the key must have an ORed instance. So we must be able to order these keys, which makes sense if you guys are familiar with maps, because we want to have some sort of system of how to look into those maps. And so by arranging them in a certain fashion, we can create bins for the map and then, have efficient lookups. And then working backwards, an argument that it takes, and I can really read it in this way. There's no problem with reading from right to left. It's not like I'm going to completely miss out on the plot of the story or something. I can see it has argument of map KV, same thing as the return type, and a map K may be V. So instead of a V, it's a maybe V. And so even just from, just to add on, my intuition is saying, I haven't looked at what this function actually does at all. I literally just copy pasted it because I was like, yeah, that looks like a complex enough type signature. But what my intuition is saying is that this is probably, so apply map, it is, I'm not really sure, but I guess with apply map, I'd be thinking that there's going to be some sort of merge between V and maybe V. And I'm assuming that internally there is some sort of function to decide how to deal with these different values. And so we might have like a just, and then if it's a just and a value, we might replace the value. But yeah, don't exactly know. This is also from the Reflex library, which I will do a tutorial on in the future, in a full-on tutorial. But yeah, so that is kind of a simpler one here. So I also have just some more complicated, and now this is where, this definitely is a bit complicated. This is also from Reflex Query Base. Note, Reflex, not Reflex DOM. And so when I see like bigger type signatures like this, or rather when I'm creating my own type signatures, I don't really often go and just read type signatures anymore. I actually did used to do that because I'm weird. But you can kind of break it down like this in terms of the arrows and the type classes. So I wouldn't, like, now we are kind of starting to get into really hard to read, even like for me, as long as I have been writing Haskell code and reading Haskell code, this is still like I have to kind of slow down and think about it. So I can see that we, and also too, so the reason this is a good, one of the points I'm trying to get across here is that, any library can create its own types, its own classes, and of course its own functions. And so Reflex is an especially complicated one in terms of its types, and that's for a very good reason. As we will see, it's very easy to do front-end development in Reflex, model complex systems that is not at all complicated for us. It's kind of like it just feels like play. So, but anyways, with this one here, so query TQMA is going to be our return type. I could, I'm going to start, the next thing I'm going to look at is just what two arguments it takes. and keeping in mind that these type variables are going to have maybe some constraints on them, and so I have another argument, query t tqma. It is, so I can see that it has the same m as my return type, same a as my return type, whatever that means. Query t, or well, the t is also the same, but the q is different. And I believe, if I recall correctly, that the q has to do with some what the actual type of the query is. But that's not really important to actually understand the type signature. I'm just going to, throw that in just in case that helps with understanding the context of what we're doing. In terms of what this function is doing at a high level, query t is basically a beautiful function, a beautiful set of functions, I should say, that it makes it just how I'll explain it is it makes it really easy to model getting data from your database in terms of how you want to use it on the front end in a type safe way. And that's the key thing. It's easy. It's not so complicated to get information from the database, but this is kind of like a pipeline, or the overall functionality of query t is like a pipeline of how to get data from the database in a type safe manner. So, AKA, you cannot, accidentally do some unsafe query to your database or expose a part of your database that you do not want to. Now, the last piece is this dynamic t query morphism. So even this part's a little bit complicated. I see that there's brackets, and inside we have a query morphism. So I can tell that query morphism is a fully applied type. Everything here everything eventually ends up being a fully applied type, but that doesn't mean that we can't have a higher kind of type, which gets applied, and then itself, as a fully applied type, becomes an argument for another complex type. And the logic for that, and how that's kind of very clear in a not theoretical sense. I don't want to use that word because I feel like it can cause unnecessary overthinking. But I guess the logic of why that makes sense is if we look at, for example, the kind of either, and then we apply either once. So we say either a. Okay, yeah, I should have to do that. We can see that it's less and less, and that now with that it is a single star. So if it's a single star, well then it fits in this star. So we could say, if we have this, and that might be a little bit more complicated way of saying it. I could go back to, either just being expecting two fully applied types, but maybe this will make it simpler because we're just going to reapply the same exact thing. And so I guess we're kind of, building up this kind of pyramid of either. And we can see that this is a fully applied type. Now, if we really wanted to get crazy, we could keep, I don't think this will actually work. Oh, actually, well, okay, there's a way I could do this. I could say type x equals this. And I could say either x, x. Oh.
And then I could, call it, and I could keep on going and going and going. But the point is that that might be hard to think about with kinds. And again, this is why I have a whole video on it, is just that a complex type, which is fully applied, can then be used as a type argument for another complex type. Because at the point that a complex type is fully applied, it's no more complex than an int or a character. And I hope that helps. So in this case, we have query morphism is fully applied with its Q and Q. And I can see that this... Well, I won't explain why this makes sense, but this Q pertains to the input Q, and this Q prime applies to the output prime. And so that's wrapped in a dynamic T. We don't need to know what a dynamic T is for the purposes of this lesson. We will actually get to that in terms of... It is a very important piece in reflex, but we will not talk about it now. All we need to know is that it's a complex type. And we can see, too, that this is actually kind of important for reflex, but again, we don't need to know why it's important for reflex, that this T is the same for all of them. So, I will say, so this is kind of a weird approach, because I haven't taught you guys any of the more, what's seen as complex classes in Haskell, and I don't think that's actually necessary, because I think this should be separated and taught before you get into these kind of complicated classes, and I think that's what makes them so complicated, is just simply when they're taught and how they are taught. As we will see, they're really actually quite simple, and I will argue to the death of me that they are just a shortcut. They are not important. I guess I'm not giving them names at the moment because I don't want you even looking them up. You could probably figure them out, but they're not important for now. And I will fight to the death that they are just shortcuts. They are just to make coding Haskell a little bit easier and less to write. So you can write some crazy function in 3 words. That is what the point of that is. But anyways, so finally moving on, we have this this list of, or I guess it's technically a tuple of constraints. And so we can see there's a constraint of monad fix. We do not need to know or care what that is at the moment. We only need to know that monad fix is some constraint which applies to M. Post build is one of those complicated type signatures, or one of those complicated type classes where it is a statement about 2 types. So what this is saying, and I'll explain it because it applies no matter how many types we have. I guess no matter how hierarchy the constraint is, that what this is stating is that there has to be a specific, in the most general sense. It's not really going to tell you, this explanation is not going to tell you what post build does. And keep in mind, you could go and read what post build does and get a sense of why there's 2 type variables. You'd really have to dig into it, come to think of it, but so it's just a statement about the relationship between T and M. And in this case, what it's actually saying is that they have to be consistent, really. They have to be consistent, and that has to do with this concept in reflex, which we'll get to, called the timeline. But I'm not going to say anything more for now. Same with, so group is just the same kind of deal as monad fix in that it just is some constraint on Q. Commutative, same old, group also on Q. Like I was saying, I guess we could even organize these like this. And that looks valid. So, and then, continuing on, same with the query Q prime. And the last kind of thing I'll say about this type signature, just in terms of really understanding it, is that, for example, let's look at Q. So if I undo what I did there and put the statements about Q and Q together, and let's say we even have another one, just show Q, which we're familiar with. Talked about in basic type classes. What this is saying is, so this is there's one thing you could look into if you want more reading and fun is the Hindley-Milner type system. And I'm not going to explain it in full depth here, but just because I don't think that's helpful. But since we have three constraints, that mean on Q, that means that we have, to satisfy all constraints, so that limits the number of options that we have. Like if you imagine a circle, and I'm just going to do this in kind of 2D, then that's the set of all instances of group. Now, if we want to further find all the instances of commutative, they would be in this set. And so we have some exclusions. And lastly, we have show, which, it would probably be almost the full size of the thing, but of the previous set. But, since it's our third class constraint that we have, we would just say that it limits even further what the range of valid types are for this equation. And keep in mind that there's, again, no magic here. What this is going to evaluate into is something without constraints. So at the end, when this is all compiled, and we have an executable program, there's going to be no such thing as a constraint. It is all going to be a very real type. And, what we're doing with these type variables to begin with is just overloading functions, and in effect creating a number of different functions. And so maybe that confuses you. It's not super important to understand, but yeah. So the core important thing to understand of the last kind of piece I'm saying is just this kind of little crappy diagram here of what defines a valid type in terms of these classes, and just the fact that when a function evaluates, it is going to have some real type. In every single case ever in Haskell is going to evaluate with a very real type. And that will be especially important to remember with reflex, because there is a ton of abstraction and overloading that happens with those classes in order to make the creators of reflex, the library's lives, a lot easier and more broad. That will make more sense when we get to reflex. Very powerful stuff. And yeah, that's it. So I will say, if you are scared easily, maybe don't go to the next part. And I think I even had a note to myself. Oh, yeah, there it is. Oh, I thought I just exposed it. But I have a monster below here, and this is like the most complicated type signature I've ever seen in my entire life. So, I just kind of wanted to do this for fun.
And this is not really simple Haskell at this point. You don't need to do this, but I just want to show you that even as complicated as this next type signature gets, it's still actually quite understandable. So I believe I got it from here. And like, oh my gosh, I can barely even read what that word is. Traverse DMAP with key with adjust requester T with. I don't know. I will never use this function in my entire life. Well, I will, but I will probably use. What I will use, actually, I can show you, is class. Requesting identity, which is still may look a little bit more complicated at the moment, but is still not too complicated. And this is still, I would say, even on the less simple side, but this is another constraint, and this is actually a language extension, but you will still see it from time to time. It's a more common language extension. And what this is saying is that there is an equality of these types. So I'm not sure exactly how to break it down here. I'm gonna leave a very high level explanation for now, because this does get into definitely some more complicated stuff. I will say, in terms of, I've used requesting identity before, and I'm still having trouble reading this. I can read it, but slowly, and I haven't had to think about what it actually means. So, I can read this. I can understand what this means, and I even still don't need to know what that means fully. So, anyways, though. The beast, and it was this lad, and I guess this one's even a bit bigger, but I think I have this one down here. So I just went through and I separated it out, and it is complicated. I cannot read this. I don't need to read this. This is a low-level function, and I am kind of very much questioning myself as I include this in the video. But this is as complicated as it gets. So I guess my point is if you can even slightly understand this, you will never come across a function that you go, I cannot parse. So anyways, let's read this. And we have a new keyword here, and this is again another language extension, like the squiggly line. We actually even have a squiggly line right here. For all is so it's called explicit for all. It has a number of different applications, and I believe there's a very good Stack Overflow answer on it if you are curious. But again, I would not worry about it. I don't use it. Not really. I've never actually seen a purpose for it. I will say Reflex uses it a lot, but it's so in the simplest, quickest explanation, it's an explicit for all, and saying that it's just giving a message to the Haskell compiler that basically, like, it's effectively just a stronger form of polymorphism. So how we think of K as being a polymorphic type variable, it's just enforcing that, making sure that the Haskell compiler knows that. And I can't speak as an expert on that because I don't use it, but I don't think you often need to use it. If you do use it,
please let me know why you use it. And yeah, but again, not really important. So we can almost even ignore it. And so what's even more complicated here, and let's go away from this for a second. We could have a function, for example, map. Map is a function. We had filter too, which we saw. You know what? I'm going to use filter because filter and zip width as well is another function. So filter is a higher order function in the sense that it takes a function as an argument. And so let's compare this to a non-example. So a non-example would be this. If we take away the brackets, and the brackets kind of help you identify that this is a higher order function. But again, the easiest way to do that is by reading from right to left. And of course, seeing brackets. So if it was this case, then this would mean that filter itself takes 3 arguments. However, in this case, where we have the brackets, what's inside the brackets is its own singular argument to filter. And so, we can even just kind of mentally think of it as being whatever the heck. Oh, that did not work. So, so filter takes 2 arguments, not 3, and one of those arguments is a function which itself takes a singular argument. And now, in typeland, nothing really fully makes sense for the sake of making sense, I suppose. But it's all about what are we actually doing in the function, and that's where the constraints and the type signature itself is really derived from, in terms of thinking. And so filter is just a function where we take some filtering function and use it to filter out certain elements in the list. So if we had a list from 1 to 10, and we wanted to look for all of the even numbers, then we could write a filter function which checks if the element that we are at is even, and if it is, then continue to keep it, or keep in the list. If not, toss it out. So that's really that. So I guess that takes us back to our kind of final destination here. And so I'm just going to read this from the end and see that it returns some requester T, which itself is still kind of complicated. That's a understatement of the year. And its final type parameter to parameterize requester T as a constructor, a type constructor, is a tuple of a DMAP with a key and value and an event T. This is also a little complicated because P, what I can see from here is that P would be the same kind as DMAP. And you might be able to see why that is. DMAP takes 2 arguments. Here we can see that P takes 2 arguments. And this actually kind of might be a new thing. Let's simplify it just a bit by saying what it would look like if it was this. So K is some type value, or some type constructor that takes v as an argument and then is fully applied. If we didn't just make this up. Going back one further, this means that p must be of the kind star to star to star, or jeez, there we go. So p, the kind of p is this. Or I guess, yeah, that would be our logical thing. So, and then that, once fully applied, is given to event, and that constructs our entire tuple, which is itself a type argument to requester t, which we will return. Event t. Now, event t also has this pkv, which we just talked about. So, but again, p has star to star to star, and that itself. Oh, my brain is getting tired. But again, you don't need to do this ever. Just literally, I'm kind of going, to the nines for the sake of, you never having to, go like, what the heck is that? And then be like, this simple Haskell channel, it failed me. So that's our argument of event t of some pkv. A dmap is another argument, and then it looks like we have a bunch of functions, including this one. And so yeah, we have, I guess, now 6 functions, which we are probably going to use on these 2 data structures. And some nested for alls. I guess this is not for all. Haha. And then yeah. So, each of these individual functions kind of breaks down in their own way. I'm just going to go through one because I don't see the point in going through every single one. At a high level, we can break this down into 6, and then I'm just going to say that we don't care about breaking down the other 5. Actually, I will break down 2, just because there is another added complexity I'm seeing. And, okay, so this one, everything starts after the dot here. You can see the dot after the for all. So, my cat is just trying to get in as I'm trying to read the signature. This is crazy. Yeah, everything after the signature is our actual core types. We can kind of forget about everything before that dot with the for all. Who cares? So it takes a KA as its first argument. I'm kind of breaking my rule. So this function itself is going to return a requester t with parameterized with the t, request, response, m, va, and that individual piece is going to take as arguments a ka and a va. Etc. And then we have here a requester t is returned, and that takes an event t, which is parameterized with a p, which is parameterized with k prime and v1. Another argument to make this requester t
of a DMAP KV1, another argument of M, which is parameterized with V2, which is parameterized with A. And so, working back outwards, if you prefer that, V2 is fully applied and then is an argument to M. And then we have another V1A, and then we have a last KA, and then the kind of added complexity here is that we have a constraint, and so this is, I believe, allowable because of, well, actually no, this is just allowable. What am I saying? We could have filter could have a constraint, for instance. Filter could have a constraint. Although, why would you do that? I mean, I don't see why you would not just say that. That seems that's typically what you'll see, but you could go like that. Of course, removing this, or it's kind of redundant. But yeah, and then that lastly brings us back to, so what do we actually have here? Let's review and put it all together. We have we return this requester team thingy, majiggy, and it has some two concrete types of DMAP and an event T PKV. And then we have a bunch of functions which are given, a bunch of functions which are used as arguments to work on these two, and some added complexity with the type class inside of the one function that is given as an argument. And then we have lastly our constraints. And so the constraints, with the exception of this beast, these are all the same in terms of what we've seen before. Really, patch actually, I believe, is as complex as post build, and that it takes two arguments. It's just hard to see because does it even take one argument, might. Oh, yeah, so patch takes one argument. And so, in this case, in the most general way of framing it, and again, this is no longer simple Haskell. I'm going to put like a warning in the video or something. Just because, you might run into this, and maybe the better name for the channel is Simplified Haskell. Yeah. So, because, you can get, with any language, you can get arbitrarily complex, but I'm just trying to, set you up for success, I guess. So, yeah, but we could, work through all of these different things and see that they make sense. This is saying that, so in the most general sense of how to read a type constraint, is saying that this statement about patch should work. I should be able to write an instance of patch for this, where this may be some extremely complicated type, but technically this would have an instance of patch. So as weird as that is, it still could have an instance of patch, and why I get the weird aspect of it is that this is kind of a almost like a
That's what I'm looking for. Like an instance of a complex type, where P is that complex type. It looks like P takes 2 arguments. Yes, P takes some K, and event T, this stuff. Everything up to here. So, yeah. And so that is as complicated as it gets. Obviously, we still have that last for all, but who cares? And we have just, if you stuck through that, we just read the most complicated type signature I've ever seen. And yeah, but the point is that once you've read one type signature, you have read them all. Thank you so much for watching. Please, especially for this one, this is like, I say the whole channel is an experiment. This has been an experiment and a half, if not 2 experiments. So, yeah. Let me know your thoughts on how this video went, if you did stick through with this more complicated last part here. And I guess I can't really say anything to people who already left. But if I could say anything to them, I'd say, please still give me some feedback, and please like, share, subscribe, all that good stuff. Anyways, have a good morning, afternoon, night, whatever you like to code. Bon voyage, and happy coding.